All right, now what we'll talk about today is doing something called point group assignment. So it ends up that if we can find certain symmetry elements within a molecule, that actually guarantees that other symmetry elements will be there. Fortunately for us, people in the past have worked out a series of names, and we can name a molecule as part of a particular point group, and we can go through and use this flowchart to decide which point group it's in, and then that will tell us about all the symmetry elements that are within that molecule. So I'll be going back and forth. I'll use this somewhat. I'll post this for you guys on Canvas. This is a flowchart here that will help you assign point groups to a molecule. There are a bunch of different ones of these that are online. I like this one. This one here, basically the entire top of the flowchart here goes through, and it helps you to figure out, do you have a very symmetric molecule, so something like that's tetrahedral, like methane, CH4, has a really high symmetry molecule, or something that's perfectly octahedral, also very high symmetry, or something that's really low symmetry. I'll show you a few of these here in a minute. So it's possible to have just a mirror plane or just an inversion center, or to have no symmetry whatsoever. All those things are possible. So the whole top of this chart here is figuring out if you have a really high symmetry or really low symmetry molecule. If it doesn't belong to either really high or really low symmetry, you start on this part over here, and then you're going to assign it to one of these 6 groups: DNH, DND, DN, CNH, CNV, or CN. So let's look at a few of these. I have a collection of these here, and I'll post this also on Canvas. Really, really low symmetry, or no symmetry molecules here first. So this guy, bromochlorofluoromethane, it has 4 different groups attached to the carbon. This has no symmetry whatsoever to it. You can't rotate it, do a reflection, inversion, any of those things to it. It has no symmetry elements at all, except its own identity. So it has that identity operation where we either do nothing or rotate by 360. And this is most objects in the universe. So most things that we look at have no symmetry whatsoever to them. CS, so something here like thionyl chloride, this has just a reflection plane. It has a single reflection plane through it. So it would go through the oxygen and the sulfur here, and it would reflect one chloride into the other. This is always going to be true if we have only 3 atoms. So 3 atoms, we can always define one plane. So hypochlorous acid here, also CS. The plane of the molecule is the only reflection plane that exists. It's also possible to have just inversion, and for these, this is going to be just one rotameric isomer, or one rotamer of the molecule. And so, for example, this structure here, I'll make it a little bit bigger. This has only an inversion center. So this is a chloride and a bromide and a hydrogen. So if I start here on the center, the inversion center, and I go left and up and out, I hit hydrogen. So I need to be able to go back and in and down and also hit hydrogen. Or both the chlorides here are in the plane. So if I go left and down, I hit chlorine. If I go up and right, I hit chlorine. So those are our really low symmetry groups. Also, it's possible, this would be the lower part of the chart. This is also a pretty low symmetry group. It would be ones that have only proper rotation. So for example, C2, this particular rotamer, so this orientation of the hydrogens for hydrogen peroxide has C2 symmetry. There's some more examples for you below. Won't go through each one of these. You can look at these. We'll get down to that bottom part where we have something like this that has C2H symmetry, C3H symmetry, D2, D3. Those are pretty rare. Get back into the more common ones here again. And then here's the really high symmetry group. So methane, really high symmetry. This has 4 C3 axes in it. Okay, all your normal molecules, all your common molecules are only going to have at most one C3 or C4, C5, those higher order axes. They're only going to have one of them in there. This has four of them for the tetrahedral point group. Likewise, we've seen this a lot in the class. This is hexacarbonyl chromium 0. Belongs to the octahedral point group. And we have, this has three C4 axes in it. So if you've got a whole bunch of C4 axes, it's going to be octahedral. And then we get into the really, really high symmetry. These are the icosahedral point groups, and the most common one that you guys would see is the buckyball here. The C60 fullerene has a bunch of C5 axes in it. So these last few that we talked about, really high symmetry groups. Okay, I'll also attach this. Won't talk about it too much right now, but this is kind of a gallery that shows you examples of each different kind of point groups. It's definitely worth looking at for you. So finally, what I want to put in the screencast is to go back to symotter.org. And it would be worth your while to go through and look at the challenge. So I'll pull down to the challenge tab here. And this is similar to something that I asked you guys about. So we have, this is 1,2-dibromobenzene. And first you have to decide, is it a linear molecule? And it's not. Linear molecules are going to be, maybe at most 4 atoms, and they have to be completely all in a line. So this is not a linear molecule. So no. Does this contain 2 or more unique C3 axes? There's no C3 axes, so this is an easy no. What's the highest order rotational axis that exists? And I see a really obvious one here. So there's a rotational axis that goes right through these carbon-carbon bonds. So there's a C2, and there's nothing higher than that in this molecule. Well, if this is my C2 axis, then I'm going to go in and investigate and see if I can see 2 perpendicular C2 axes. So this up and down one is my primary. Well, I could investigate going right through here, but that's not going to work because that would bring these bromides up here, and there's not a bromide up there to reflect to. So that's a no to perpendicular C2 axes. Does it contain a horizontal mirror plane? Well, as soon as we define the primary axis, which is up and down, horizontal then would be this way. So horizontal will not work. If I try to put a horizontal mirror plane here, it would, again, reflect these bromines up to the top, so that doesn't work. No horizontal. Vertical, well, that's another choice. So vertical will contain this primary axis. So I do believe that I can put a mirror plane right through here. That looks good to me. It reflects bromine into bromine, carbon into carbon, and hydrogen into hydrogen. So that's a yes. And so then I've determined that this point group should be C2V. And it is. Let's do a few more together. Here's a much more symmetric molecule, just simple benzene. It's not linear. That one's easy. Does it have a C3 axis? Yes, I can do a 1/3 of a turn. It has one C3 axis right here in the middle that would move, say this this CH over to here. It has one, but it does not have 2 or more. So no to 2 or more. The highest, oh, this is pretty high symmetry. So this has a C6. I can do 1/6 of a turn. So C6. And what you want to do is right away now, so the primary axis always is the one that is up and down. So remind yourself it goes right through the middle. It's going to go up and down. Now this hydrogen is pointed out at me. Okay, so perpendicular to that, do I have C2 axes? And I only have to find one. There's 6 of them there, but I only have to find one, and the other ones will be there. So there's an axis that goes right through the middle of the molecule. And yes, it has perpendicular C2s. There's one that would go through hydrogen, carbon, carbon, hydrogen. So yes to perpendicular C2s. All right, and again, so my primary axis goes up and down here. So, and this molecule is flat, and so there is a horizontal mirror plane. I can say yes to that. So I've determined this to be D6H point group, and yep, it is D6H. All right, here's one of those really high symmetry. Here's methane again. So it's not a linear molecule, no. Does it contain two or more C3 axes? Yes, it sure does. So there's a C3 axis that goes through this CH bond and would move those other ones around. Or I can turn it up this way and I would have an axis that goes through here. There's four of them total. There's one that goes through each CH bond, yes. It doesn't have any C5 axes, no. Does it have C4 axes? That would need to be 1/4 of a turn, so no. Does it contain one or more reflection planes? Yes, it does. I could do a reflection plane through this hydrogen, carbon, and hydrogen and reflect the hydrogens into each other. Yes. Does it contain an inversion center? To have an inversion center, I need to be able to do the opposite of any operation. So if I set this like a tripod, so here would be my camera and here would be my three legs. I go up and I hit a hydrogen, so I would need to be able to also go down and hit a hydrogen. So that is a no. It does not have an inversion center. And so this is the TD point group. Let's see one that does have an inversion center. This is just the solid. This is an octahedron. This is the platonic solid of an octahedron. It's not linear. Does it have a bunch of C3 axes? It does. There's probably the most obvious orientation to see them down those faces. So yes, it does have C3 axes. It does not have any C5s. No. Does it have C4s? Yes, it has a bunch of C4s. So I can orient it this way, and now I've got this square. So that's 1/4 of a turn would leave me okay. So it's C4. Does it contain an inversion center? It also contains an inversion center. So if I start at the very center of the molecule and go up, or start at the center and go down, I hit the same point. If I start in the center of the molecule and go right and up, or left and down, I hit the same point. So yes, it has an inversion center. So this is the octahedral point group, which is good. It's a octahedron. All right, let's do one more. Hydrogen cyanide. So now, I think I can finally answer this question as yes. So HCN, it has a rotation axis and infinite folds, so any tiny infinitesimal rotation I want to do about this axis, I can do. It has this, what's called a C infinity axis, yes. Does it contain an inversion center? Well, I'd have to be able to start on carbon and go right and hit the hydrogen and go left and hit the same atom, so no. Because on the left it's nitrogen, on the right it's hydrogen, so no. So this would be the C infinity V point group, and that is correct. All right, so I suggest that you guys go through and practice these. All parts of this website are really good. There's a gallery where if you want something that's a particular point group, you can go in and just select it to look at the symmetry elements. So you can go something like this. This is also tetrahedral symmetry. You can go over here and visualize where the axes are. So like the C3, I've put on all the C3s on here. So methane would be easier. I put on all the C3s. I have all these different C3 axes. So the gallery is good, the tutorial is good, and the challenge is good. So this will be something I'll ask you guys to do on the exam, is to do something with a symmetry element, maybe assign it, or follow what it does to the labels, and also to assign the point group of a molecule.